So welcome to our first talk today, and I will talk about open optimized VVC implementations on ARM architectures. VVC, I think I can be very fast here. It was finalized almost 2 years ago, so probably you're aware that's the successor to the HEVC video coding standard, and was developed to provide 50% bitrate reduction on average for over HEVC, with a focus on versatility, so different applications from video beyond standard and high definition. It supports improved adaptive streaming, enabling open GOP adaptive streaming, but that's a different topic we will hear more about this year. Gaming, screen sharing, and immersive video. So open optimized implementations. Right after VVC was finalized in July 2020, we made two software implementations of VVC available on GitHub. One is the VVEnc, which is a versatile video encoder. At the time now, it's the most efficient and fast open video encoder for VVC. It allows fast offline encoding with random access. So it's not designed to do like low latency live encoding. It's more for offline VOD cloud encoding. That's the envisioned use case of VVEnc. VVDEC is the versatile video decoder. It's the fastest fully compliant open VVC decoder available right now. It enables UHD 10-bit decoding on a laptop and HD live on a mobile, which we will see later in the results. So why ARM and how to run VVEnc and VVDEC? So ARM, if you think about, traditionally used to be the CPU in mobile. So mobile phones, tablets, maybe TV boxes. But that changed recently with, for example, Apple introducing the Apple Silicon, which is based on an ARM design. It has the M1, the M2 right now for laptops and workstations. We have the ARM Neoverse Silicon design for service and cloud instances. In this talk today, I will focus on the laptop and workstation Apple Silicon and a bit on mobile. One big plus of that architecture is energy efficiency. So they are, as you will see, reasonably is understating it. It's really fast, and also the energy consumption is pretty fascinating low. But this is probably a different topic that's worth analyzing as well to check which encoding efficiency you get per watts. That we will not touch due to time constraints. So energy efficiency is a big motivation to check it. Then the implementations in video coding, be it encoder, decoder, typically heavily rely on single instruction multiple data, or called SIMD optimization. So that's a parallelization on an instruction level. So it allows you to perform filtering kernels, for example, not one by one, but just to process the whole tabs of a filter in parallel with these instructions that are supported by modern CPUs. By using SIMD in the VVEnc encoder, we can achieve up to 3 times speed up, and this is for free because it's just parallelizing and just not sacrificing efficiency. And we developed the whole framework with VVEnc and VVDEC using x86 intrinsics from SSE 4.2 to AVX2. And having these intrinsics, that allowed us to use a great framework called SIMD Everywhere, or SIMDE, which allows you to automatically translate to other SIMD operations like a WebAssembly, or you can use it to generate or support ARM Neon optimization. So Neon are the multimedia extensions for the ARM design CPUs. So this is pretty easy. So it just take less than half a day to have that running using the automatic translation, which is amazing. However, it's easy, but it has some pitfalls, as you will see. The experimental setup we use here in the results that I will go present, I chosen roughly like 3 categories. One is a workstation. Here we have chosen the M1 Ultra from the Apple Studio, which has 20 cores. 16 of that are high efficiency cores or performance cores. This is the 60p, and the 4 ones are efficiency cores, which are used for simple tasks. And yeah, you will see that 16 cores can be fully exploited, while the low or the efficiency cores are not performing as well, which is expected because otherwise they would have been called performance cores. They use 20 threads, so there's no simultaneous multi-threading, or I guess Intel calls it hyper-threading. So the x86 representative system in that category is a Xeon Gold CPU. It has 28 cores, and with hyper-threading offers 56 threads. So the OS on which we run the test is macOS 13.2 and Ubuntu 22.04. Compilers listed here. The SIMD extensions supported by the M1 Ultra are Neon, and the Xeon supports AVX 512, which is not supported by VVENC. So there's still a bit potential that you can exploit here. We only support up to AVX2 because this is the most recent extension that is supported by almost all CPUs, x86, and AVX 512 is still a bit niche in the CPUs nowadays. So this is currently not supported, but for example, there are studies on what AVX 512 enabled in for x265, and you get, like, I guess if I remember correctly, something about 8% speed up, but also surprisingly the energy consumption increases there as well. So this is something we need to keep in mind for the future, to also observe energy consumption, and that's also on our roadmap. This is very interesting, especially in the context of greening of streaming and so on, to observe in the future. Then for the laptop, we have an M1 Max from an Apple MacBook Pro and an i9 CPU from a Dell laptop. The M1 Max basically is one SoC of the 2s from the Ultra, which has 10 cores, 8 performance cores and 2 efficiency cores, and the i9 has 6 performance cores at a very high frequency at 5 gigahertz max, and 8 efficiency cores, but still at 3.4 gigahertz. 20 threads, which is, yeah, you see that the performance cores, they can have simultaneous multi-threading, while the efficiency cores do not have, so that's why you have 2 times 6 plus 8 means 20 threads. And it supports up to AVX2, while the M1 still supports Neon. On the mobile, we have a Snapdragon ARM-based CPU with 8 threads supported and also Neon optimizations. The configuration for the encoder, VVENC, we used version 1.7. The current version is 1.8, but it's just incrementally getting faster. But it's pretty representative, the results here of the current version. For the laptop, we used 8 threads when encoding, and on the workstation, we used 20 threads. Why 20? Because typically there's more supported, more threads available, because the parallelization approach in VVENC is somehow limited. It's not like you use 50 frames and it gets 50 times faster. At some point, in some number of threads, the efficiency of the multi-threading decreases or saturates. So that's why if you go beyond 20 threads, you won't get any more significant speed up. You just burn CPU power. So that's why we limit it for the workstation that can have a higher amount of cores to be used for parallelization to 20 threads. In addition to that, we use wavefront parallel processing, which is like processing CTU, so the basic block size in parallel, and 2x2 tiles. We divide a picture into 2x2 tiles to have a better scaling and make the most of the 20 threads used. For VVDEC, we used 1.6. and followed overall the JVET common test conditions you can find in that document here, T2010. It consists of 5 HD and 6 UHD sequences, always uses 10-bit coding. Even if we have an 8-bit sequence, we code it as 10-bit. It has random access points each second. So this is the intra period is roughly 1 second and uses the QPs from 22 to 37, which results in very different bit rate, as you will see in the results. And the Unix time utility was used to measure the runtime. So first, the impact of vectorization. What we see here on the left side is what speed up or how much faster the encoder gets if you use SIMD. And compared to not using SIMD, which is here meant by scalar. So you see on the ARM platform, which is here it was the MacBook, the laptop platform where we measured that. The Neon optimization SIMD gives you between 2 and 2.2 times speed up, while if you look at the x86 system, which is the i9 laptop, if you use AVX2, you can get really up to 3%, 3 times speed up. So there's still a bit room for improvement for the Neons. This is what I meant. This is very easy to automatically translate it to ARM for Neon, but we figured out in doing a deeper profiling that, for example, some functions in VVENC it was the chroma scaling function of the Luma mapping and chroma scaling loop filter, which got slower after automatic translation. So you really have to be careful and check and profile each part that is automatically translated. So by just disabling SIMD for that part, we get even faster. So this is work in progress and what we still need to do. But just for a first shot, half a day, less than half a day work, I think this is quite a good speed up to be achieved for an encoder. Then I have the SSE 4.2 here as a reference because this is the comparable instruction set that you have in Neon. So AVX2 has provided more optimizations that are not available via ARM Neon extension. So you have to be fair, you have to compare it with SSE 4.2 because more than what SSE 4.2 can do is not achievable with ARM Neon. So that's why, to be fair, you really have to compare it with 4.2 because the other instructions are not available on ARM. The other test, which is quite interesting here to do, is that on the Apple Silicon, you can run x86 compiled code, and it emulates using the Rosetta 2 emulator. And this already performs quite well. So just compiling it with x86 SIMD, only SSE 4.2 is supported here. In this emulator, you still get a bit more than 1.6 times speed up. So this is showing that the emulator is quite efficient. On the right side, because the numbers on the left side are averaged, and just to give you the full picture, on the right side I plotted the slowest HD and the fastest UHD sequence. And here you can see that the speed up for UHD can go even up to 4 times using AVX2. But here you can see it also strongly, heavily depends on the bit rate. So the higher the rate, the less speed up you get by SIMD. This can be explained by the fact that the higher the bit rate it gets, the more time you have to spend in quantization and entropy coding, and there's no speed up or no SIMD optimized code in VVENC for these parts. So the overall impact of SIMD decreases the more the bit rate increases. This is more drastic for the AVX2, so for the x86 case, the dashed line, the solid line there represents the neon speed up, which is below that. And then if you consider HD, the speed up is also even lower. So this is what you can get. So you are in that range of speed ups you can achieve with applying these optimizations either on x86 with AVX2 or on ARM with Neon. So VVENC encoder runtime is in relation to the HEVC reference software, but in order to give you a better picture, you have the relation to the X265. So the faster preset of VVENC is comparable to the slow preset of X265 on an x86 platform. So this is just to give you an idea. So we will focus on this preset. I have to come to the end, I see. Okay, so bottom line, you can look it up in the paper, find all the detailed results here, but these are the frames per second. So frames per second on an x86 workstation, and on the ARM workstation, you can see that on the ARM, the FPS number significantly increases. So this is a very powerful system for the VVC encoder here. For the laptop, it's not that big, that difference. So they are more comparable in performance. There's a low decoding preset on a mobile. You can achieve like very high frame rates even on a tablet. This is the some information on how it's run on a tablet. There's FFmpeg integration of both ongoing. They are available via Homebrew, so you can easily install it without needing to check it out and compiling it. There's a link with instructions how to build these patches, so you can easily build your own FFmpeg and use VVENC and VVDEC. So just to summarize it, the OpenVVC implementations VVENC and VVDEC have been ported and tested on ARM platforms, which enables fast UHD encoding on an M1 Ultra and M1 Max, so on the MacBook Pro and the Mac Studio. You have live HD and UHD decoding on an ARM tablet and on the ARM-based laptop. The fully automatic translation works pretty well as a first shot, but has to be fine-tuned, and this is something that we need to do in future work, optimizing and hand-tuning it for the SIMD components for ARM, assessing the energy efficiency, and also the next thing is to evaluate the performance on ARM-based servers, which is also nice because they can provide up to 128 cores. So thank you very much.
Thank you. We'll take only one question. Okay.
I hope the answer
can
will
you
be
go back to the slide number 11? So just a quick question. Okay, one before that. I think it's a different numbering.
This one?
This one, yeah. So you present HM 16.24. Can you say like where more or less will be located VTM 17, like the last version of reference VVC?
Yeah. So in terms of performance, VTM is a bit below slower. Okay. So the slower preset of VVENC is actually a bit more efficient than VTM right now. So we managed with some non-normative optimizations to get a better efficiency than VTM in the slower preset. And so this is the BD rate axis, and on the encoding time axis, you would be by 700, so 7 times.
Okay, I understand. Okay. Thank you. Okay.
Okay, thank you.